Okay, now let's introduce normal distribution. So, as we mentioned about random variables, we know that some random variables are uniform or uniformly distributed, but some are not. And in practice, typically data do not really spread uniformly. Most of the natural situations have the fact that values tend to be close to the center. Okay, like heights of people, weights of dogs, lengths of leaves, etc. Most of the people would have heights that are close to the center, right? Only some people are tall or short, and only very few people are extremely tall and extremely short, something like that. For performance, it's the same thing. Number of cars crossing a bridge, sales made by salespeople, etc. Typically, there are some kind of central tendency, or all kinds of errors. Like if we are estimating consumer demands, mostly we will have some errors, but mostly the errors would be close to zero if we are not making some systematic mistakes, etc. So hopefully that we can have a distribution that is useful and that is appropriate to capture that kind of central tendency. And hopefully that distribution is flexible enough so that it can fit into all kinds of different random variables, all kinds of different situations. And that's something we have. That's normal distribution. So a normal random variable follows a normal distribution with mean mu and standard deviation sigma with its PDF something like this. Okay, obviously we don't really care about this formula. All we want to say is that okay, there is a formula. There is a PDF for normal random variables to decide the shape of the normal curve. All we need to do is to specify mu and sigma, the mean and standard deviation of the normal curve. Okay, once we do so, then we're going to have a normal curve. That normal curve may be different for different mu and different sigma, but it has some properties. So first, most of the natural values will be close to the center. The curve will look like this, so that if we have a center, most of the data will be around the center. Okay, we know this curve is the PDF, which is the likelihood. So the likelihood of values around zeros are high and others are low. So that's why values tend to be happening close to zero. Okay, that's the first thing. And also it is symmetric. So values may be too high or too low, but the probability for being too high and too low are basically the same if we are using the same standard. And we say it's bell-shaped because it looks like a bell. It looks like a bell. Okay, and then mathematically we would write x follows a normal distribution with parameters mu and sigma. So this is important. Once we decide mu and sigma, then we have a normal curve. The important thing is that if we give you different mu and different sigma, the curve will be different. And we know how to expect the change on the curves. The first thing is that if we increase the expected value mu, then that's going to shift the curve to the right. Like here, we have two curves, one blue, one green. Their center is at 10, or their mean is at 10. But if we change to another one, which has mean 12, then the curve basically shifts to the right. Okay? And that's reasonable because when the mu goes up, the value tends to be high, so the curve moves to the right. At the same time, if we increase the standard deviation sigma, that's going to make the curve flatter. And the flatter here simply means it's harder to predict the outcome because extreme values now have higher probabilities to occur and the center values now have lower probabilities to occur. So like if we compare the blue one and the green one, Their mean is the same, but their standard deviations are different. And when the blue one has a higher standard deviation, the curve looks flatter. And that means the variance or the fluctuation or the standard deviation of the blue one is higher than the green one. So let's look at some examples. Again, now let's consider the temperature example. Suppose x is a normal curve, okay? Or we say we want to estimate, we want to approximate the distribution of x by a normal curve. In that case, we probably, according to past information, past experience, say that, okay, I believe the temperature would be a normal random variable with mean 25 and a standard deviation 5. In that case, I fully characterize the distribution because I know the PDF, the height of the PDF of each single value. Okay, in that case, now I can calculate some important probabilities. For example, suppose that there is a policy that the lecture must be cancelled if it is too cold and if it's too high. So in either way, we need to cancel the lecture. If that's the case, then basically we want to calculate the probability for x to be lower than 15 or the probability for x to be 35. And we know the two events, less than 15 and greater than 35, either of them has some probability to occur. So we need to sum them up. And because this curve is symmetric, right? And the center is at 25. So we know this length is 10 and that length is also 10. So because the curve is symmetric, this part and that part, those two areas must be identical. So the probability for x to be less than 15 and the probability for x to be greater than 35, they must be the same. So we only need to calculate 2 times the left tail probability, and turns out it's around 5%. We're going to, if we want to calculate that number, we just need to use software. So that's not a big deal. But here, the important thing is that when we are asking about this probability, the probability for the lecture to be cancelled, we calculate the 2 tail probabilities. Okay, so among all those standard normal random variables, one is important. One is called the standard normal random variable or standard normal distributions. If the mu is 0 and the sigma is 1, then we say this normal distribution is a standard normal distribution. So obviously there are so many normal distributions and we pick one to be standard. Okay? The reason that we want to have this standard normal distribution is because it helps us state an important theorem about normal distribution. Is that all the normal distributions can be transformed to the standard normal distribution. Or say it in another way, for all the normal distribution or all the normal curves, they can be found to be equivalent to the standard normal distribution. And the way is here. Suppose I give you capital X, which is normal. Then if I ask you to characterize the distribution of x minus mu divided by sigma, then that's going to become a standard normal distribution. Okay? So what does that mean? If I give you a normal distribution and I tell you that its mean is mu, standard deviation is sigma, then I can shift the distribution by subtracting mu from all the possible values, and then normalize or standardize all the values, scale the standard deviation to divide all the possible values by sigma. After I do so, I'm going to get another normal distribution, and that turns out to have 0 and 1 as the mu and the standard deviation. This transformation is called standardization. Okay, let's see some examples. So suppose I have x, which is normal with mean mu and the standard deviation sigma. we know that we have something called z-score, right? And the z-score is x minus mu divided by sigma. It measures how far this value is from the mean, using the standard deviation as the unit of measurements. Okay? For example, if z is 2, then we know the value x is 2 standard deviations above the mean. And we sometimes say that x is 2 sigma above the mean. And sigma just means standard deviation, right? So in that case, we probably want to ask, well, is 2 sigma above the mean? Is it far or is it close to mean? I don't know. Or I want to ask, well, what's the probability for some value to be that large, to be 2 sigma above the mean? I want to know that. So let's consider these two examples. Suppose I have x, which is normal, with mean 100 and the standard deviation 20. So that's a normal distribution. And y is normal, but with mean 90 and the standard deviation 10. Okay, so I have two normal curves. For each of them, I want to ask, what's the probability for a value to be 2 sigma above the mean? Or for x, I'm asking what's the probability for x to be above 100 plus 2 times 20. Okay? Or for y, I'm asking what's the probability for y to be above 90 plus 2 times 10. Okay? I want to ask what's the probability. And the interesting thing is that given the standardization result, the standardization theorem we mentioned in the previous page, we have this. What's this? The probability for the variable x to be 2 sigma above the mean is this one. What's this? This is to subtract each term by 100 and divide each term by 20. Okay, so we can see this equation is indeed true because we are doing the same thing for the two sides of the greater than or equal to. And then that just means what? The left-hand side can be expressed as a normal random variable, and the right-hand side can be expressed as 2 because that's the outcome of the equation. For y, we can do the same thing, and turns out it's also 2. So what does that mean? That means these two probabilities must be the same. These two probabilities must be the same. Or if we try to visualize it, x, suppose it's something like this. Okay, so here is 100, and the standard deviation is 20. If I'm going to plot y, I know its mean is going to be smaller, and it's going to have a higher central tendency because the standard deviation is smaller. So I probably have a curve like this. Okay, the mean is at 90, and it's more centered instead of dispersed. And then I'm asking about two probabilities, right? I'm asking two probabilities for x to be 2 sigma above its mean, and for y to be 2 sigma above its mean. And then the probabilities are the same. So a conclusion is that if I'm asking about what's the probability for a random variable, a normal random variable to be k sigma away from the mean, then that answer would be the same for all the normal distributions. Okay? Given any normal distribution, as long as I ask you about the probability for the value to be k sigma away from the mean, the answer is the same. So that means normal distribution in some sense are all equivalent or can be transformed from between each other. Okay, so lastly, consider our classroom temperature example. We know that x is mean 25 and standard deviation 5, and we know the probability to cancel the class is about 5%. Okay, so that means for a normal distributed data set, the probability of being 2 sigma away from the mean is just 5% according to this. Or that means if we are only talking about one tail, okay, being above or below the mean, then the probability would be half of 5%, so that's 2.5%. So that means if we are considering the probability for a value to be 2 sigma away from the mean, it's not so likely. It's just 5% for any normal random variable. Okay? Then recall our 3 sigma rule for detecting outliers. If that distribution is normal, then the probability of being 3 sigma away can be calculated as less than 1%, just about 0.25%. So that means it's really, really rare. So if your data follows a normal distribution and you find a value that is 3 sigma away from the mean, then it's very likely that there is something wrong, or it's really a rare event. That's something to look at because it's not a normal situation. Okay, that's why the distance of 3 sigmas is suggested. Okay, that's the end of today's lecture. Thank you.